Hello everyone, today let's take a look at a basic optimization question, QP22, where we have 4 people, A, B, C, and D. They're trying to cross this river. The only way to cross the river is by an old bridge, which can hold at most 2 people at a time. So being dark, they cannot cross the bridge without a torch, of which they have only one. So each pair can only walk at the speed of the slower person. A takes 10 minutes to cross, B takes 5 minutes, C takes 2 minutes, and D takes 1 minute to cross. So what is the minimum amount of time for all of them to get to the other side? So not the best drawing, but if this is my bridge right here, I have my 4 people, A, B, C, and D, and then this is supposed to be a torch. So if 2 people cross together, right, they all have varying times to cross this bridge. They're going to need to bring the torch, and they're probably going to want to go 2 at a time, in which case they will walk at the speed of the slower person. So for instance, if A and B go across, well, A is slower than B, so it's going to take both of them 10 minutes to cross. Now, once 2 people have crossed this bridge, right, we're still going to have C and D on the other side in this case, right, and they need the torch to cross. So B is going to have to go back with the torch and bring it to them, right, and then we can have 2 more people cross, maybe something like this, and then someone's going to have to again bring the torch back for our remaining person. So that's what it's going to look like. So now we just basically have to find what is the sequence of people going across that bridge such that the time is going to be minimized. So let's think about that for a sec. Well, first thing to note is that C only takes 2 minutes and D only takes 1 minute, right? Well, B and A take 10 minutes and 5 minutes respectively, right? So C and D take much less time to cross this bridge than A and B do. So initially you might think that we might want our 2 slowest people to cross the bridge together, right? But then that's going to cause a problem because now B has to bring the torch back at B's speed, which is going to be much longer than C or D. So that kind of just implies that we're going to want C or D to be our runner back and forth with this torch. So given that, let's just do a few examples. Let's say that first of all, we send B and D across together. That's going to take 5 minutes. Let me keep a running sum right here. So that's going to take 5 minutes because B is the slower person, right? So it's going to go at the rate of the slower person. Now, once we've sent B and D across, we're going to want to send D back with the torch because obviously they are faster. So if we send D back with the torch, that's only going to add 1 minute here. Now we still have to get A across this river, right? That's going to be our biggest limiting factor. A is going to take 10 minutes. So let's send them with our fastest person. So again, D can bring the torch back for C. So if we send A and D over together, right? Well, that's going to add 10 minutes to our travel time. Now from here, we're going to want to send D back over because they're our fastest. That's going to add 1 minute to our travel time. And now when C and D come over together, that's going to take 2 minutes because C is the limiting factor in this case where C takes 2 minutes. And then everyone will be on the other side. So in total, it took us 10 plus 1 plus 1 plus 2 plus 5. So it took us 19 minutes in total if we do it this way. But can we do better? Well, the first problem you might note with doing it this way is that we have this 5-minute time and then we have the 10-minute time, right? So we sent A and B across separately. But we could get rid of this extra 5-minute case if we just sent A and B over together, right? Because then that 10 right here would kind of tank this 5 as well. So we probably do want to send A and B over together, but remember the problem with that is if we send them over first, well then B is going to end up being our runner and that's just going to be way too long, right? We want C or D to be our runners. So we kind of want A and B to go over together, but we don't want B to be the runner. So basically what we can do instead of that is let's maybe just have C and D go over together first, right? That's going to take 2 minutes instead. Now let's have our faster person D bring the torch back for these other 2, right? So that's going to add 1 minute. And now we can send A and B across together because we know that we have a fast runner on the other side. So if we send A and B over together, that's going to add 10 minutes to our total, right? So plus 10. But now that we have a faster person over here, we can just send C back with the torch and that's only going to add 2 minutes, right? And now we can send C and D over together yet again, and then that's going to add 2 minutes. So what do we get in this case? We get 10 plus 2 plus 2 plus 2 plus 1, and this is 17 minutes. And 17 minutes is better than the 19 that we got before, right? And this actually ends up being the optimal answer. You can end up going through all the cases, but this right here will be the optimal strat. So we basically had C and D go over together, so we always had a runner on the other side in order for when we sent over B and A together, right, in order to get rid of that extra 5 minutes, right, that we still had a runner on the other side to bring the torch back. So because C and D are so much faster than A and B, this will end up being our optimal strat here. So the fastest amount of time for everyone to get to the other side is going to be 17 minutes.